Hi, welcome to my talk on our paper Enabling Ahead Prediction with Practical Energy Constraints. My name is Chester, and this is done in collaboration with Aniket and our advisor, Professor Yale Patt at University of Texas at Austin. Unfortunately, I cannot come to Tokyo in person to present this paper. If you have any questions after the presentation, feel free to email me for additional questions. Single-thread performance relies on highly accurate branch predictors to deliver correct path instructions to the processor backend. These predictors use large lookup tables and a complex logic to generate the prediction. And as a result, it takes multiple cycles to generate such a prediction. In order to sustain the wide frontend that is typical in the CPU today, products use a multi-level predictor scheme. We have a simple predictor that returns the result at the end of the first cycle. These predictors have extremely tight timing constraints and therefore has a very poor prediction accuracy. We also have a high accuracy predictor that has a multi-cycle predictor latency, 3 cycles in this example, as this is the most typically found on products. If the two predictors agree with each other, then the next prediction can start on the next cycle, and we can enjoy both the low latency of the single cycle predictor and the high accuracy of the multi-cycle predictor. However, if the two predictors do not agree with each other, then the multi-cycle predictor would issue a pipeline flush at the end of cycle 2 and start the next prediction at cycle 3. This would effectively stall the prediction pipeline for 2 cycles every time these two predictors do not agree with each other. We studied the performance impact of the predictor latency. In this study, we used a 1K entry 2-bit saturating counter as the single cycle predictor, and Tage from the 64 kilobyte Tage SCL as the 3-cycle overriding predictor. We varied the predictor latency without changing the actual predictor implementation. A predictor latency of 1 means that the Tage predictor is used as the single cycle predictor. Our experiments show that every additional cycle of latency translates to around 2.5% performance decrease. If we can completely remove the predictor latency, we can gain a 6.5% IPC improvement. In the multi-level prediction scheme, the prediction of branch N uses the history and PC of branch N, which is only available at the beginning of cycle 0. This means that we only have a single cycle to produce the prediction of branch N in order to drive the prediction for the next branch. Academia has long proposed ahead prediction as an alternative to the multi-level prediction scheme. Ahead prediction solves the prediction latency problem by starting the prediction earlier with the PC and history of a prior branch, thus hiding the prediction latency from the prediction pipeline. In this example, the prediction of branch N now uses the history and the PC of branch 0. While this solves the prediction latency problem, this has a prediction accuracy problem. As you can see, the branch N is now predicted without information about branch 0, branch 1, all the way to branch N-1. Prior work noticed that if we're skipping N branch ahead, then there must be 2 to the N possible missing history patterns, since each one of the n branches could either be taken or not taken. Prior work reads out multiple entries from each table, each corresponding to one of the possible missing history patterns. Prior work uses that to generate 2 to the n predictions with the ahead history. When the prediction is finally needed, all the intermediate branches has been predicted at this point. And we can use the predictions of the intermediate branches to select which one of the 32 predictions is the final prediction. While this solves the prediction accuracy drop with ahead prediction, this has a huge prediction energy problem. Notice that in this case, for each prediction, we now have to read 2 to the n times more bits. Cacti shows that the per prediction energy for an ahead distance of 5, which is necessary to cover the 3-cycle prediction latency, is 14x compared to baseline tape. The number of entries read out per prediction increases exponentially as ahead distance increases, making the problem worse as we used to use a longer ahead distance to cover an even larger branch predictor. We start our research by asking the question, just how many missing history patterns are there? We conduct experiments using the SPEC 2017 benchmarks. For each branch, we collect the patterns of the next 5 branches. And at the end, we count the number of patterns observed for each static branch. Our experiments show that, on average, about 30% of the time, we only observe one pattern within the next 5 branches. And around 90% of the time, we observe 8 patterns or less. This is significantly less than 2 to the 5, 32. And that is because most branches in the program are biased or unconditional. We repeat this experiment with 64 bits of history. We wish to count the number of patterns for each control flow that leads to a branch. And again, we aggregate the final numbers at the end of the simulation. In this experiment, we notice that the number of missing history patterns are significantly less when we use history. Specifically, on average, over the SPEC 2017 benchmarks, more than 70% of the time, we only observe one pattern, and we only observe 5 patterns or more 1% of the time. Benchmarks with many hard-to-predict branches like MCF, DeepSGen, Lila, and XZ exhibits significantly more number of missing history patterns compared to the rest of the benchmarks. This is because skipping over a predictable branch does not introduce a new pattern, while skipping over an unpredictable branch increases the number of patterns. We provide a detailed analysis of this in section 3 of our paper. Now let's talk about our ahead prediction scheme. Since there are only a few patterns for a given ahead history, we force the entries corresponding to the same ahead history to be in different tables. This allows us to read out all the entries from the same ahead history without reading multiple entries per table. We also explicitly tag each entry with the missing history pattern that led to the entry. Here is an example of how prediction works with our ahead predictor. The indexes and the primary tag are generated from the ahead history. The entries highlighted in red are the one entry read out from each table. Just like prior work, we still generate a prediction for each one of the possible missing history values by duplicating the selection logic of Tage 32 times. For each slice of this selection logic, it only considers entries that are both primary tag hits and secondary tag hits for that particular missing history value. For most missing history values, since there are no primary tag hits and secondary tag hits, it will follow the prediction out of T0, the bimodal table. For missing history 1, there are 1 primary tag hits from T2 that's also a secondary tag hit. In this case, the prediction out of T2 will be followed for the missing history pattern 1. And for missing history pattern 31, we observe 2 primary tag hits from table T1 and table T21, and we default back to the Tage algorithm to pick which one of the 2 is followed for missing history pattern 31. Notice at this point, we do not know which one of the 32 missing history pattern will provide the final prediction for this branch. By the time the direction of the branch is finally needed, at this point, all intermediate branches have been predicted and will use their prediction and targets to generate a selection logic to pick which one of the 32 prediction is the final prediction for this current branch. Notice that the 32-to-1 mux happens at the final cycle when the prediction is needed. Since this is just a 32-to-1 mux, it does not impact the critical path. We use a hash function to compute the secondary tag, which is used to select the final prediction. This allows us to decouple the secondary tag size with the ahead distance, meaning the secondary tag can be as small as 1 bit and can sometimes be even more than the ahead distance. We later show results of how the size of the secondary tag changes the overall performance and energy consumption. The results of our ahead predictor is that our ahead predictor achieves comparable performance to the baseline Tage and provides a 4.4% IPC improvement. The 3 benchmarks that benefits the most from our scheme are exchange, B-waves, and ROMs. These benchmarks have high MPKI from the single cycle predictor and low MPKI from the baseline Tage. As promised, here's the study of our ahead predictor and how our ahead predictor's secondary tag size changes the overall performance and energy consumption. If we match the ahead predictor ahead distance and the secondary tag size both at 5, then our ahead predictor can provide 4.4% IPC improvement, while only increases the per prediction energy by 54%. If we only use 1 bit of secondary tag, our ahead predictor can still provide 2% of IPC improvement, but only at 10% of per prediction energy increase. That concludes my talk. If you have any questions after the talk, feel free to email me. Thank you.